Are we alone? This question is in some ways as old as the starlight that travels through the eons to reach us. Since the earliest civilizations, our ancestors have looked up at the night sky in wonder, their imaginations fired by the flickering lights overhead. Today, armed with the power of modern science and technology, we still await the answer to this age-old question. But our goal is not just to find primitive life, but to discover the whispers of civilizations that might share this grand cosmic stage with us. The Breakthrough Listen Project, the most ambitious search for these whispers, techno-signatures, is pushing the limits of our hearing in an attempt to capture the murmurs of extraterrestrial life. As we stand at this crossroads of discovery, several teams of scientists in the Breakthrough Listen study and other SETI projects have already published several scientific papers moving us closer to answering this question. So, how close are we to the goal in this grand quest? What non-trivial decisions have been made to ensure a seamless search for signals and improve our chances? Let's get to the bottom of it. In our celestial odyssey to unlock the mysteries of life beyond Earth, scientists have charted two major paths across the cosmic seas: the search for biosignatures and the search for technosignatures. Each path offers a unique lens through which to view the potential for life in the universe, guided by the principles of astrobiology and the advanced technologies at our disposal. Biosignatures, the chemical fingerprints of life, serve as beacons in our search for biological activity on distant worlds. These signatures are not just markers, but signs of complex interactions between living organisms and the environment. Every molecule, from the oxygen and ozone created by photosynthetic life forms to the methane and carbon dioxide produced by biological and geological processes, carries a story of potential life. The James Webb Space Telescope, JWST, with its unprecedented sensitivity to the infrared spectrum, is our most advanced scout in this endeavor. Using transmission spectroscopy, JWST can analyze, dissect light from distant stars as it passes through the atmospheres of orbiting exoplanets. This light bears the fingerprints of various molecules, each absorbing certain wavelengths and leaving behind a spectral signature that JWST can detect and analyze. Peering into the depths of space, JWST searches out these spectral lines with precision, allowing us to infer the presence of water vapor, carbon dioxide, methane, and other potential biosignatures in the atmospheres of exoplanets. This method not only hints at the possibility of life, but also provides insight into the atmospheric composition, climate, and habitability of these distant worlds. Parallel to the search for biosignatures is the search for technosignatures, the hallmarks of advanced technological civilizations. Unlike biosignatures, which indicate the presence of life in any form, technosignatures suggest a leap to complexity, where life has evolved to use and manipulate its environment in profound ways. From radio signals to megastructures orbiting distant stars, technosignatures embody the potential to detect not only life, but also societies that may have mastered the art of cosmic communication. The pursuit of technosignatures spans the galaxy. Initiatives like the Breakthrough Listen Project utilize vast networks of radio telescopes to listen to and eavesdrop through space. These telescopes scan the sky for narrowband radio signals, anomalies in the natural cosmic radiophone that may indicate deliberate transmissions from intelligent beings. Biosignatures are whispers of life embedded in the fabric of a planet's atmosphere, providing a glimpse into invisible worlds orbiting distant stars. Among the vast number of potential biosignatures, 4 stand out for their significance: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and mysterious unexpected combinations of molecules. Oxygen, The breath of life on our planet and its companion, ozone, form the first pair of key biosignatures. On Earth, oxygen is a byproduct of photosynthesis, the process that formed our atmosphere and allowed life to thrive. The presence of ozone, a molecule formed from oxygen by the sun's ultraviolet radiation, provides a protective layer shielding the surface from harmful radiation. The discovery of these molecules in the atmosphere of an exoplanet could indicate the presence of a thriving biosphere, perhaps similar to our own. Phosphine and ammonia, less common but no less intriguing, represent a second pair of biosignatures. Phosphine, a gas associated with anaerobic ecosystems on Earth, has been proposed as a potential marker of biological activity on other planets. Ammonia, another molecule with biological ties, may indicate the presence of life, especially in environments where it's not expected to exist in significant quantities due to non-biological processes. Methane and carbon dioxide form the third cornerstone of our quartet of biosignatures. Methane, a potent greenhouse gas, can be produced both biologically by organisms such as methanogens and abiotically by geologic processes. Carbon dioxide, a critical component of Earth's carbon cycle, is a product of respiration and volcanic activity. The simultaneous presence of methane and carbon dioxide, especially in unexpected ratios, may hint at biological processes in nature. Finally, with the fourth point, we move into the realm of unexpected combinations of molecules, methane and carbon dioxide, which cannot be stably present in more or less large quantities simultaneously without being transformed into other substances. Such combinations defy conventional expectations and point to the possibility of life functioning based on alien biochemical processes. The James Webb Space Telescope, JWST, humanity's most advanced observatory, is designed to study the atmospheres of exoplanets in search of these very biosignatures. Using transmission spectroscopy, JWST studies light from a star as it passes through a planet's atmosphere during its transit. When light passes through atmospheric gases, certain wavelengths are absorbed by the molecules, leaving behind a spectral fingerprint that JWST can detect and analyze. On the other hand, technosignatures, like the fingerprints of advanced civilizations, offer a different path in our quest to discover not just life, but societies that have reached a level of technological sophistication, perhaps similar to or even superior to our own. Unlike biosignatures, which hint at the mere presence of life, technosignatures speak of the ability of civilizations to alter the environment on a grand scale, communicate across the stars, and harness energy in ways we're only beginning to imagine. Technosignatures cover a wide range of signals and structures, from radio waves unintentionally emitted by a planet's communication networks to deliberate beacons aimed at the stars, from colossal energy collectors known as Dyson spheres to the barely perceptible glow of city lights on the exoplanet's night side. These signatures, if detected, will not only indicate the presence of life, but will also provide deep insights into the technological capabilities of alien civilizations. Our own planet is a prime example of a world teeming with technosignatures. Every radio broadcast, every satellite, and every piece of space debris orbiting the Earth creates a symphony of signals that, to the distant observer, unmistakably indicate the presence of an advanced civilization. The very fabric of our daily lives, from global communications networks to space probes venturing into the unknown, generates a cascade of signals that radiate out into space, making our presence known to all who can hear us. But why are technosignatures a more accurate way to search for technologically advanced civilizations? The answer lies in their specificity and the intentional or significant nature of the signals and structures they represent. While biosignatures can occur from simple microbial life to complex ecosystems, technosignatures clearly indicate a level of technological development and intent. The discovery of a technosignature not only confirms the existence of life, but also indicates that this life has crossed the threshold of cognitive and technological capability, engaging in activities that leave an indelible mark on the cosmic canvas. Breakthrough Listen was launched in 2016 with an ambitious mission to scour the cosmos for signs of technologically advanced civilizations. The project represents one of the most comprehensive searches for alien technosignatures ever undertaken. Armed with state-of-the-art technology and unprecedented scope, the project utilizes some of the most powerful radio telescopes in the world, including the Green Bank Telescope and Parkes Observatory. These colossal ears, tuned to the quiet whispers of the universe, can detect a range of signals, from faint radio emissions from distant stars to potential transmissions of extraterrestrial origin. At the heart of the mission is the desire to detect technosignatures, signals that, by their nature, can only be produced by technological means. These can range from narrowband radio signals that differ from the natural background noise of space, to powerful laser pulses that cut through cosmic clutter. The project had previously focused on the Milky Way galaxy for strategic reasons, to begin the search in our cosmic neighborhood, where such signals may be strongest and most detectable. The Milky Way, with its billions of stars, provides fertile ground for such work. Each observable star is a potential sun for other planets. Each planet a potential cradle for life as we know it, or life yet to be imagined. The project was originally designed not just to search for signals in our galaxy, but to explore in depth the nature of life and intelligence in the universe. Sifting through the cosmic expanse of the Milky Way looking for signs of life is akin to searching for a single word spoken in a whisper in the middle of a bustling metropolis. A galaxy of about 100 billion stars can easily conceal the signals of other civilizations. The task of monitoring such a vast array of targets for technosignatures is monumental, not only because of the large number of stars, but also because of the complex array of cosmic phenomena that can obscure or mimic the signals we are looking for. The problem is compounded by the limitations of our current technology and the limited resources at our disposal. Even with the most advanced radio telescopes, we can only listen to a small fraction of the stars in the galaxy at any given time. Huge distances dilute the signals, making them fainter as light years pass, and various natural cosmic phenomena such as the emission from pulsars and nebulae add further complexity to the search. In the face of these challenges, astronomers and scientists have looked beyond the familiar boundaries of the Milky Way to the wider universe. By observing galaxies as individual entities, each made up of billions of stars, we can try to pick up the cumulative signals of advanced civilizations. This extragalactic strategy is based on the premise that a sufficiently advanced civilization can harness technologies that affect its entire galaxy, from building megastructures like Dyson spheres to harnessing the energy of supermassive black holes. Such grandiose endeavors could lead to technosignatures that, in theory, could be found in vast intergalactic voids. The transition to extragalactic studies comes with some challenges, from even greater distances to the need for more sensitive instruments and more sophisticated methods of data analysis. Nevertheless, each galaxy observed and each dataset analyzed brings us closer to understanding whether we're truly alone in the universe or part of a grander galactic world. Extragalactic exploration is exactly what Carmen Choza and her team did in 2023. Using the Robert C. Byrd Green Bank Telescope, the team has embarked on an ambitious mission to observe the centers of 97 nearby galaxies, studying them for 5 years. This work, one of the largest of its kind, used to search for narrowband Doppler drift in 4 frequency bands from 1 to 11 gigahertz. The goal was to detect signals that could come from civilizations capable of using energy equivalent to that of a Kardashev Type II civilization. The most important aspect of this study was the implementation of the TurboSETI pipeline, a sophisticated tool designed to search for Doppler drift. This pipeline played a crucial role in analyzing the vast amount of data collected during the study. To combat the persistent problem of radio frequency interference, called RFI, which often mimics extraterrestrial signals, the team adopted an on-source, off-source cadence pattern. This method involves alternating between observations of a target galaxy, on-source, and a nearby region devoid of the target, off-source, and is repeated 3 times for each galaxy. Because RF interference and localized noise are present regardless of the telescope's pointing, they'll appear in both on-source and off-source observations. In contrast, a true astronomical signal should only manifest itself in observations from the source and not in the observations beyond the source. This approach helped to distinguish real astronomical signals from terrestrial interference, which improved the reliability of the results. Despite careful methodology and advanced technology, the study faced significant challenges, primarily due to radio frequency interference. The team's innovative radio interference mitigation strategies, including signal injection and recovery tests, were crucial in differentiating terrestrial and potential extraterrestrial signals. These efforts emphasize the difficulty of finding technosignatures, especially since signals must be significantly more powerful than those detectable within our galaxy to be considered extragalactic. The exhaustive search resulted in 6,034,313 hits across all observed galaxies. These matches represent cases where the data analysis pipeline has identified signals that potentially stand out from the background noise and may be of interest for further study. From the original 6,034,313 matches, further refinement and analysis using a computer algorithm narrowed the field to 1,519 events of particular interest. These events were then scrutinized by the research team, which attempted to distinguish potential extraterrestrial signals from the all-pervasive RFI noise. Despite the complexity, the team eventually concluded that all 1,519 events were associated with terrestrial sources, or natural cosmic phenomena. However, the work done by Chosa and her team not only illuminates the path we've traveled, but also beckons us to new horizons. The ability to reanalyze data through the subtle prism of machine learning promises us a chance to uncover signals that previously remained obscure or were perceived as noise. This changing landscape of SETI research, constantly enriched by technological innovation, invites us to look deeper. As we move forward, armed with improved tools and a deeper understanding of the challenges that await us, the search for extraterrestrial technosignatures continues. In the meantime, we'll be eagerly awaiting new opportunities to solve the mysteries of the cosmos. In a universe filled with mysteries, one question towers above many others. Are we alone? This riddle, also known as the Fermi paradox, attempts to answer our understanding of the cosmos and our place in it. Named after physicist Enrico Fermi, who during a casual dinner conversation reflected on the silence of the universe, the paradox confronts us with a stark contrast. On the one hand, the sheer number of stars, like grains of sand on Earth's beaches, suggests a high probability of extraterrestrial civilizations. On the other hand, our sky remains eerily silent, devoid of any sign of these civilizations. Despite advanced technology and the ever-expanding reach of space, not a single whisper or wave has reached us from deep space. This silence raises profound questions. What are the barriers that prevent potential civilizations from reaching out or crossing the stellar expanse? Can the vast distances of the universe or the fleeting nature of civilizations explain their absence? Or does the answer lie in the very fabric of the emergence and survival of life in space? Among a sea of stars, our solar system provides a glimpse of the possibilities and limitations of life beyond Earth. Ice moons and distant worlds harbor oceans beneath their frozen crust, mirroring the early conditions in which life is thought to have originated on our planet. These hidden oceans, protected from the harshness of space, may be the cradle of life and intelligent beings. However, these creatures may very likely be incapable of traveling beyond their icy boundaries, or even unaware of such a possibility. Just such a hypothesis was recently proposed, forcing a rethinking of the variables of the Fermi paradox. Let's take a closer look at how much it's affected the answer to why we still have not been able to hear the echoes of alien civilizations in the universe. The silence that reigns in space is an enigma that has baffled minds for decades. Imagine a universe where technological marvels and interstellar communications fill the void between the stars. Such are the expectations of our science fiction and logical predictions based on the Drake equation, which estimates the number of active, sociable extraterrestrial civilizations in the Milky Way galaxy. However, when we delve into the vastness of space, the reality is strikingly different. The expected intergalactic discourse remains only an expectation. The Fermi paradox asks a deceptively simple question. There are billions of stars in the galaxy, many of which have Earth-like planets, but where is everyone? This fact has definitely caused perplexity among scientists and the public alike, leading to numerous theories attempting to solve this mystery. One common explanation is the Great Filter Theory, which suggests that at some point in the evolution from a planet to intelligent life capable of colonizing galaxies, there is a highly improbable step that few, if any, civilizations overcome. On the other hand, the Zoo hypothesis suggests that advanced extraterrestrial beings deliberately avoid contact with us to allow for natural evolution and socio-cultural development, much like zookeepers observing animals in a sanctuary. Strangely, despite our sophisticated antennas and listening devices, we've still not picked up the slightest whisper from space. This leads one to speculate that perhaps our listening techniques are not adapted to alien communication methods. Or worse, that intelligent life is extremely rare or short-lived due to self-destruction or cosmic events. Especially given the vast expanse of space we've already scanned, it's hard to draw any other conclusions. Why is this happening? It may suggest that our knowledge is incomplete now, or we're listening in the wrong way and at the wrong time. However, perhaps things are much simpler than they seem. One recent intriguing proposal is the fishbowl worlds hypothesis. The traditional search for extraterrestrial life often focuses on Earth-like conditions, planets in the habitable zones of their stars, with liquid water and atmospheres capable of supporting life as we know it. However, such a view can be too narrow and fail to take into account life that does not meet our Earth-like expectations. The fishbowl worlds hypothesis proposes a radical shift in the search for life. According to it, life thrives in subsurface oceans completely enclosed by a thick layer of ice. These worlds offer a stable environment protected from cosmic hazards such as radiation and meteor strikes, favoring the development and evolution of complex ecosystems in isolation. This theory draws inspiration from the work of scientists such as Alan Stern, whose contributions to space exploration have shed light on the mysteries of icy celestial bodies in our solar system. For example, the New Horizons mission discovered intriguing features on Pluto and its moon, Charon, that suggest the presence of subsurface oceans, as well as the possibility of similar conditions even in the colder regions of the Kuiper Belt. And in general, our solar system has moons such as Enceladus and Europa, orbiting Saturn and Jupiter, respectively. Geysers spewing water vapor and ice particles into space observed by instruments such as Cassini hint at a dynamic, active environment beneath their icy crust. But how do these icy moons and dwarf planets affect the fishbowl world's theory? Well, the key lies in understanding the complex interplay of gravitational forces, radioactive decay, and perhaps even hydrothermal vents on the ocean floor, all of which may contribute to the creation and maintenance of subsurface oceans. In such an environment, life as we know it, or even life forms beyond our current understanding, could find a way to thrive, isolated but protected from the harshness of space by a thick layer of ice. In these secluded ecosystems, life could thrive without the ability to gaze at the stars or contemplate the universe beyond their icy confines. This begs the question, how could such isolated creatures communicate or even imagine a reality beyond their own? This fact is definitely puzzling because it shatters our preconceived notions of what an advanced civilization might look like. On this basis, we can assume that the universe may be teeming with life hidden in such natural shelters. Perhaps our galaxy is full of these quiet, isolated worlds, whose inhabitants unknowingly share the cosmos with us. Beneath the icy shell of distant worlds, the concept of communication takes on a new dimension, far removed from our earthly perceptions. In these hidden oceans, life forms can develop unique methods of communication that are profoundly influenced by their secluded environments. On our planet, the ocean depths provide a glimpse of how life can adapt to the perpetual darkness of the subsurface. Marine species such as whales and dolphins use sound to communicate over vast distances of up to several thousand miles, a method that's efficient and effective in the dense environment of water. This terrestrial analogy suggests that creatures in the hidden oceans of icy worlds may also rely on sound or other forms of non-visual communication, negating the need for technology such as radio signals. In the absence of light, these creatures could have developed advanced echolocation abilities similar to those of cetaceans on Earth, allowing them to see through sound. Knowledge acquisition in this context would be fundamentally different, potentially focusing on nuanced acoustic information rather than visual or electromagnetic signals. It's quite possible that these mysterious beings, thriving in their secluded worlds, have a deep understanding of their environment, yet remain ignorant of the cosmos around them. However, the vast universe, with its myriad worlds, presents not only opportunities for life, but also formidable challenges for civilizations seeking to reach the stars. Among these challenges, the gravity of home planets is a colossal barrier to the dream of interstellar exploration. This aspect introduces another critical factor into the Drake equation known as the exoplanetary escape factor, which assesses the feasibility of space travel from worlds not like our own. Exoplanetary escape factor is an important addition to the Drake equation, offering a method for quantifying the difficulties an extraterrestrial civilization might face in trying to escape the gravitational grip of its home planet. The equation for the escape velocity of a planetary object shows that larger and more massive planets pose a huge problem. Earth, whose escape velocity is 11.19 kilometers per second, serves as a baseline for comparison. For instance, a hypothetical super-Earth with a mass much greater than our own would have a prohibitively high escape velocity, making conventional space travel an insurmountable task. Imagine the scale of engineering and energy required to break away from a planet far greater in size and mass than Earth. Escape velocity from such worlds would be much higher, requiring propulsion systems far beyond our current capabilities. Such worlds may be rich in life and even have advanced civilizations, yet remain eternally isolated and their skies eternally out of reach. These civilizations may develop in complete ignorance of the cosmos, and their technological advances limited to the confines of their own world. However, it is conceivable that these civilizations could explore alternative routes into space. Innovations such as space elevators, orbital rings, or even harnessing the energy of planetary rotation could provide solutions to the difficult problem of high flight speeds. However, these technological advances will require materials and energy sources far beyond what we currently consider possible. In addition, it further complicates the version about the development of life on icy moons and dwarf planets. Enclosed in a thick ice shell, these worlds provide protection and stable conditions for life, but they also create additional layers of isolation. For intelligent beings living in such environments, the very concept of space may be incomprehensible, hidden behind impenetrable barriers of ice and rock. It begs the question, how would these creatures perceive their place in the universe? And what colossal effort would it take for them to break through the ice ceiling and venture into the unknown? It would be logical to assume that in the heart of a world bound by the heavy chains of gravity or by a dense shell, the pace of life and the trajectory of civilization follow a lesser-known path. Here, the attention of intelligent life forms would be visibly directed inward, toward their world. In such societies, environmental constraints may lead them to focus on mastering their immediate surroundings, optimizing their habitat, and exploring their world in depth. In such a case, there's nothing strange about their lack of connectivity. Being able to go beyond their planet is necessary for the concept of going into space to be a foreign idea, both figuratively and literally. Now, as we stand on the threshold of a new era in space exploration, our eyes are turned not only to distant stars, but also to the icy guardians of our own solar system. Several ambitious missions will be heading to this icy expanse in the coming years. Europa Clipper, scheduled for launch this October, targeting Jupiter's moon Europa. Dragonfly, planned for a 2028 departure to Titan. And several proposed concept missions targeting Saturn's moon Enceladus are at the forefront of this search. These celestial bodies, once considered frozen wastelands, are now seen as prime candidates for the search for extraterrestrial life in our solar system. These missions are equipped with advanced technology to penetrate ice sheets and explore the vast oceans beneath them. By analyzing the composition of water plumes ejected into space, studying the geology of the ice, and mapping the subsurface oceans, scientists hope to find signs of life, or at least the conditions necessary for it to exist. In any case, so far, there's no direct evidence of extraterrestrial life in our system. However, in the next decade, this veil will be opened and will shed new light on this issue. The data collected may provide empirical support for the idea that life can exist in conditions far different from those on Earth, and that the universe may be teeming with invisible life, much of it hidden in such isolated fishbowl worlds. However, if we find nothing, we may have to scrap the idea and start looking elsewhere for clues. One thing is clear: our search, whether it uncovers vibrant alien ecosystems or stark voids, will forever change our cosmic perspective, propelling us into the next chapter of human discovery. There are countless untold stories in the universe, but one mystery veiled in the shadows of distant suns stands out prominently among many others. This discovery invites us to look beyond earthly boundaries and ponder untold possibilities. This is the story of Kepler 22b, a planet that's not just wandering in the void, but basking in the sweet spot, its star's habitable zone. Here, in this delicate balance, all conditions exist to ignite the magic of life, for the water to flow freely and the atmosphere to hold the secrets of existence. Discovered by the gaze of the Kepler Space Telescope, Kepler 22b invites us to ponder what worlds may lie beyond our own, to question our understanding of life and our role in the universe. It makes us dream of new horizons, of distant shores where humanity may one day set foot. Today we'll embark on a journey of discovery to unravel the mysteries of Kepler 22b and the countless other worlds that await us beyond our reach in the limitless expanse of space. In its search for Earth analogs scattered throughout the galaxy, The Kepler Space Telescope has become a pioneer, a celestial cartographer mapping the unknown. Initially, Kepler's mission was very clear: to observe the vastness of the Milky Way, looking for the faint twinkle of stars dimmed by the passing of planets in their orbit. Equipped with the most sensitive photometers, the telescope patiently watched the light of more than 150,000 stars. Among them, a pattern emerged: the rhythmic fadings of a particular star, not unlike our Sun. This was the first hint of Kepler 22b, a planet moving carefully around its star and briefly eclipsing its light, as if playing cosmic hide-and-seek. This discovery was a real event. The analytical skill required to sift through huge datasets and pick out planetary transits from the cacophony of cosmic noise was immense. It was akin to detecting a faint brightness difference caused by a moth flying in front of a lighthouse beam from thousands of miles away. The method of transits, Kepler's main tool, is a deceptively simple but very powerful technique. This method is based on the subtle interactions of planets orbiting their stars, passing in front of them for a moment and casting a small shadow, which then causes a slight dimming of the star's light. It's this faint, fleeting shadow that astronomers look for, a sure sign of a distant world orbiting its star. The elegance of the transit method lies in its simplicity and the wealth of information it provides. When a planet passes in front of its star, it blocks some of the starlight, causing a measurable dip in brightness. This dip, detected by instruments such as the Kepler photometer, is carefully analyzed to reveal not only the presence of the planet, but also its size. The amount of obscured light tells us how large a planet is compared to its star. Moreover, the regularity of these brightness variations reveals the planet's orbital period, the time it takes to complete one orbit around its star. This rhythm of disappearance and reappearance allows scientists to calculate how far away a planet is from its star, which provides crucial information about the planet's environment and its probability of habitation. This method also opens a window into the planet's atmosphere. When a star's light passes through a planet's atmosphere during transit, certain wavelengths of light are absorbed by atmospheric gases. By studying these changes in the star's spectrum, astronomers can determine the chemical composition of the planet's atmosphere, finding fingerprints of molecules that may indicate the presence of water, oxygen, or even signs of biological activity. The discovery of Kepler 22b was a watershed moment in the search for Earth analogs. It highlighted the incredible potential of our technology and the perseverance of scientists. This discovery has moved us further along the path of space exploration, opening new chapters in the history of the search for worlds that could one day become a second home for humanity. In the variety of cosmic interactions between planets and stars, there is a delicate region, a narrow band where conditions are just perfect, where the hope of life as we know it lingers in the darkness. This region, known as the habitable zone, is a cradle for potential life, a haven where water can exist in a liquid state, neither boiling under the fierce light of a star nor freezing in the cold expanse of space. Imagine a world very similar to our Earth, located inside this life-supporting belt. Here, the heat from the star is neither too intense nor too weak, bathing the planet in soft light. And this is where Kepler 22b is, orbiting serenely in the habitable zone of its star, a prime candidate in the search for Earth-like conditions, and possibly life beyond our solar system. Just as Earth thrives in the Sun's habitable zone, Kepler 22b enjoys a similar privilege, orbiting at a distance where temperatures can allow lakes, rivers, and oceans to exist. The presence of liquid water, the universal solvent of many chemicals, is crucial, for it is in water that the chemistry of life unfolds. Water is the stage on which the drama of life is played out, from the simplest bacteria to the most complex forms of flora and fauna. Yet only the presence of water in a liquid state is one of the many conditions necessary to sustain life. What have we learned from analyzing this distant world? And is it so open to the theoretical presence of humans on it? As we dive into the mysteries of Kepler-22b, we embark on a journey of discovery, piecing together the puzzle of this distant world through the lens of our own Earth. With each observation, scientists are getting closer to understanding the fundamental nature of this distant planet, its size, its composition, and the very air that surrounds it. It's these factors that will help shed light on the presence of the basic components that may make this distant world a cradle for life. So, what are these factors? At the forefront of the search for life is, of course, the presence of liquid water, the cornerstone for all known biological processes on Earth. As we already know, Kepler-22b, which occupies a privileged position in the habitable zone, receives from its star a flow of energy that suggests that the temperature may be favorable for maintaining water in a liquid state. While the presence of liquid water is a promising start, the composition and behavior of Kepler-22b's atmosphere remains crucially unknown. Enveloping the planet, the atmosphere is the most important determinant of environmental conditions affecting temperature and surface pressure. Because the planet is in the habitable zone of its star, the theoretical presence of an atmosphere similar in composition to Earth's, rich in nitrogen and containing the requisite amount of oxygen and trace gases, could mean a temperate climate and stable water cycles similar to those that have nourished life on our home planet for billions of years. However, the range of possible atmospheric scenarios is enormous and shrouded in uncertainty due to our current technological limitations in directly observing exoplanet atmospheres at such great distances. If Kepler-22b's atmosphere tends toward a denser, carbon dioxide-dominated composition like that of Venus, this could lead to a greenhouse effect. In such a scenario, any potential water would exist as supercritical vapor at extreme pressures and temperatures. Conversely, an atmosphere that's too thin and free of greenhouse gases could turn Kepler-22b into a frigid world where water exists only as ice and the surface is exposed to harmful cosmic radiation. The equilibrium temperature of the planet, estimated at a comfortable 72 degrees Fahrenheit under Earth-like atmospheric conditions, indicates the possibility of an environment with ideal conditions for Earth-like life. However, if one were to go to the other extreme and create a Venus-like greenhouse effect, the surface temperature could soar to a scorching 860 degrees Fahrenheit, which would likely preclude the existence of life as we know it. Things get even more complicated. The elemental recipe for life goes beyond just water and the right atmosphere. Life, as we know it, is intricately woven from a variety of chemical elements, with carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur playing major roles. Sun-like stars, including Kepler-22, are G-type stars, and typically have similar proportions of hydrogen and helium, with a small amount of heavier elements playing a primary role. However, during planetary system formation, the distribution and concentration of materials in the protoplanetary disk around the nascent star influence the further composition of the forming planets. Temperature gradients in this disk lead to condensation of different materials at different distances from the star, which affects the composition of the planets. Once a planet is formed, its composition can be altered by differentiation, the separation of different materials within the planet, resulting in the formation of distinct layers, such as the core, mantle, and crust, and geologic processes such as volcanic activity and plate tectonics. So while direct measurements of the chemical composition of Kepler-22b are beyond our capabilities, the diversity of elements in the universe and the planet's location in a habitable zone can only hint at the exciting possibility of the presence of the building blocks that create the basis for the complex chemistry of life. While we wonder whether the planet's atmosphere might contain a protective layer like ours, or whether it's a dense, oppressive cloak trapping heat as a result of the greenhouse effect, and what the planet's chemical composition actually is, one thing we know for sure: the last, fourth parameter necessary for life is in almost perfect agreement. The complexity of life must necessarily be fueled by energy, and the presence of Kepler-22b in the habitable zone ensures its constant supply from the host star. This energy, which powers photosynthesis on Earth, could drive the fundamental biological processes necessary for life on this distant planet. The characteristics of a star that is slightly cooler and smaller than our Sun, but similar in many ways, provides a stable source of light and heat. Against the grand landscape of the cosmos, Kepler-22b stands out as a beacon of possibility, a world where the basic ingredients for life as we know it can come together. Yet the true nature of this distant planet remains shrouded in mystery, reminding us of the vast unknowns that await us as we continue to search for the secrets of the universe and the potential for life beyond our solar system. The search for signs of extraterrestrial life is the cornerstone of our celestial explorations, compelling us to venture into the unknown with hope and scientific rigor. As we turn our eyes toward distant worlds like Kepler-22b, the next generation of telescopes and space missions are poised to pierce the cosmic veil, inviting us to peer into the atmospheres of these distant planets and learn their secrets. At the forefront of this cosmic quest is the James Webb Space Telescope, the most sophisticated and powerful space telescope ever built. With unprecedented resolution and sensitivity, the JWST is designed to observe the universe in the infrared, enabling it to detect the faint reflections of light from the earliest stars and galaxies and, crucially, the atmospheric signatures of exoplanets. The JWST suite of instruments carefully analyzes light passing through the atmosphere of exoplanets as they transit their host stars. This process, known as transmission spectroscopy, will allow scientists to decipher the composition of the atmospheres of these worlds in search of characteristic signatures of molecules essential for life, such as water vapor, oxygen, and methane. The mission of the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018 and complementing JWST, is to survey the brightest stars near Earth for transiting exoplanets. Building on the legacy of the Kepler mission, TESS is casting a wider net, revealing many new worlds for further study. Among them, planets that share characteristics with Kepler-22b will be prime targets for detailed atmospheric analysis, opening up new opportunities to search for biosignatures. Coming down to Earth, the Extremely Large Telescope, or ELT, which, when completed, will be the world's largest optical telescope, will be another powerful tool in the search for alien life. The ELT's colossal mirror, located atop Cerro Armazones in Chile's Atacama Desert, will collect light from distant exoplanets, allowing direct images and spectroscopic studies of their atmospheres. Its advanced instruments will be able to detect even the faintest chemical fingerprints, further expanding our understanding of such distant worlds. Looking ahead, proposed missions such as the Habitable Exoplanet Observatory, HABEX, and the Large UV Optical IR Surveyor, LUVOIR, promise to push the boundaries of exoplanet research even further. Equipped with advanced technology such as coronagraphs and star shades, these observatories aim to directly image exoplanets by dissecting their light to reveal the molecular composition of their atmospheres in unprecedented detail. The hunt for alien life embodied in exploring such planets continues to inspire and stimulate the human spirit, reminding us that the search for life beyond Earth is more than just a scientific endeavor. It's a profound exploration of our place in the cosmos. As we stand on the threshold of discovery, our thoughts drift to the distant world of Kepler 22b, a planet in the nourishing embrace of its star's habitable zone. Here, in this hypothetical realm, we imagine the possibilities such a world might hold. Could it be that the hilly landscapes of this distant planet are home to a diversity of alien flora thriving in the soft light of Kepler 22? Could it also be that its seas are teeming with life, with forms both strange and outlandish, adapted to the unique conditions of this distant world? And what is humanity's potential role in such a world? For now, it's hard to imagine, but these dreams are underpinned by the relentless pursuit of knowledge that defines our current path in exoplanet exploration. As we gaze into the heavens with instruments such as the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the upcoming Extremely Large Telescope, we continue to push the boundaries of our understanding. Each discovery adds its own piece to the great puzzle of the cosmos, revealing the diversity of worlds that inhabit our galactic neighborhood. The future of exoplanet exploration promises to deepen our understanding and knowledge of distant worlds and redefine our place in the universe. As we stand at this crossroads of imagination and discovery, we remind ourselves that the search for life beyond Earth and the understanding of humanity's future potential among the stars is a reflection of our deepest desires to explore, understand, and reconnect with the vast, wondrous cosmos that is our home.